let's talk a little bit more about value and uncertainty. And the right method to find the uncertainty is always going to depend on how you found the value that you're finding the uncertainty of. So if you found the value by, say, measuring, so going directly and measuring a quantity, then you find its uncertainty by, for if you're measuring, by type B methods. If you found the value by averaging a whole bunch of different values, then you will find the uncertainty of the average by type A methods. And that, I want to just emphasize that the uncertainty is going to be the uncertainty of the average value. It's not the uncertainty of the individual values that you use to make the average value. We'll see how that plays out in the results from the free fall lab. If you graph to get the value, say you're looking at the slope or maybe the y-intercept, then you use a fitting program like the line estimation function that we've been using in Google Sheets. And then finally today, if you calculate the value, so for example, you measure time and distance and you're interested in the velocity, then you do what is called propagation to find the uncertainty. So what you're going to do, what the correct method is to find the uncertainty, is always going to depend on how did you get the value. So type B for measuring, type A for averaging, some kind of statistics fitting program like line estimation if you graph it, and then propagation if you're doing a calculation to get the value. So let's take a closer look at what propagation looks like. So let's talk a little bit more about propagation. And the general formula is if you've got something, an equation that you're using to calculate what you're interested in, that'll be R. And that equation that you're using to calculate R, it depends on maybe some value X and some value Y. So this just means that R, it's a function and you plug in X and you plug in Y to get whatever the value of R should be. If that's the case, then the formula to get the uncertainty of R is equal to the square root of what is called the partial derivative of R with respect to the first thing you plug in, with respect to X, times the uncertainty that X has, and we square that whole term. And then we do the same thing for Y, the partial derivative of R with respect to Y times the uncertainty associated with Y. And take the square root of everything. But if you've never heard of partial derivatives before and you're like, what is going on? That's okay. You don't actually really need to know much about partial derivatives for our purposes. You can think of them as just regular old derivatives as far as calculating them. So here you take the derivative of R with respect to X, or the derivative of R with respect to Y. But fortunately, for most of the cases we'll be using, somebody's already done this for you. So say that R is some constant times something with uncertainty. So that's a constant. And that X has uncertainty. So that's how we write uncertainty U of X. If that's the case, then the uncertainty of R is going to be that constant times the uncertainty of X. So it's just proportionate to that. So an example might be if you're finding diameter. And diameter is 2 times the radius. And so if you happen to know what the uncertainty of the radius is, then you can find the uncertainty of the diameter. The uncertainty of the diameter, so that's our R, diameters are R. 2 is the constant, so the uncertainty of the diameter would have 2 And then it would be times whatever this thing is that has uncertainty. So in our case, that is times the uncertainty of r. So this is how you would find the uncertainty if you were calculating the diameter from a radius that had some uncertainty. The next case that you might have is what if you're adding or subtracting something? We'll call that all sum. So say your function that you're trying to find depends on two things, x and y, and you add x or you subtract x, doesn't matter, either one is fine. If that's the case, then your uncertainty of this new value r is going to be the square root of each of the two uncertainties squared. So we're going to add those uncertainties in quadrature. So the uncertainty associated with x, that'll be squared, plus the uncertainty associated with y. That'll be squared too. And it doesn't matter if this is a plus or a minus. You always add the uncertainty because you don't get less uncertain adding two things with uncertainty. The uncertainty always goes up. So an example here, maybe you're adding, you're trying to get a full length, but you had to measure it in two pieces. So you measured length 1 and length 2, and both of these guys, you measured them, they have a type B uncertainty, and now you're adding them to get this full length you're interested in. In that case, the uncertainty of big L, the full length, would be the square root of the uncertainty of little l1, that whole thing squared, plus the uncertainty of little l2, that whole thing squared. And one thing I want to quick emphasize is this is not u, the uncertainty times L, this is the function, the u of L. So this whole thing, this u parentheses L1, all of that is a single number. It's the uncertainty. So don't get confused when you're plugging that in. This whole thing inside the square, that's just a single number. All right, and the final formula that we've got worked out is what if you're multiplying or dividing things, and we call that product of powers, or POP. So in that case, you're going to have a formula. You're going to calculate the value that you want, r. It's going to depend on two things that's got uncertainty, x and y. And that'll be times a constant. And remember here, a constant, the c, is something that doesn't have uncertainty. So it's like a 2 or a pi or something that we know absolutely to 100% precision. And then we multiply it by something that has uncertainty. We'll call it x. And we take x to some power. And then something else that has uncertainty. We'll call it y, and it's to some other power b. So if this is the kind of formula you get, you're using to calculate your value, you calculate its uncertainty, the uncertainty of the value r, and you multiply it by the value itself, so r, times the square root of the fractional uncertainty, so that is the uncertainty of x divided by the value x, and then you multiply it by its power. So x is to the a power, so we multiply by a, and we square that whole thing. And then we do the same thing for whatever this y is. We're going to multiply by its power. In this case, y is taken to the b power, so we put a b there. And then we multiply by the uncertainty of y over y and square that. So that's the formula. So let's do an example. An example might be the centripetal acceleration. It depends on the speed squared divided by the radius, and we can rewrite this in exactly this form. So first of all, do we have some constant that doesn't have uncertainty that we're multiplying by? Well, sort of, I guess 1. So it doesn't usually show up, but c in this case, it's 1. And let's make our speed, this first thing, this x, the first thing that's got uncertainty. So we'll write v squared, that's like x to the a power. And then finally, we have the radius that presumably we measured or got somehow, and it's got some uncertainty. So that's being like our y. So it'll be radius, and what power is it to? What's the b here? Well, we're dividing by the radius, so it's -1. So r is like our y in the general formula here. I'm going to erase those up. All right, so now how would we get the uncertainty of acceleration if this is the formula we use to calculate the acceleration? Well, the uncertainty of the acceleration. First thing we're going to do is, remember, acceleration is like our r in the general formula, so we will plug in the value of the centripetal acceleration and then take the square root. And first thing with uncertainty, that's velocity. And first thing we need to do is get the power of whatever our first thing with uncertainty is. In this case, it's 2. A is 2 here. So multiply by 2, and then do the fraction, the uncertainty of speed over the speed itself, the speed value. So uncertainty of speed divided by the speed. Square everything, including that power. Next, we do the same thing for the radius. So the power of the radius, the b in this case, that's -1. And then we do the uncertainty of the radius divided by the value of the radius, and we square that whole term. So what we're doing here is just sort of matching the thing we're calculating, the r, that's the centripetal acceleration. The first thing with uncertainty, that's the speed. It's to the second power, so that's our x and our a. The next thing with uncertainty is the radius, and it's to the -1 power, so that's our y and our b. And then we just go ahead and plug it into the formula. Given this is the way we calculate a, the uncertainty of the acceleration is the acceleration times the power of the speed times the fraction of the uncertainty of the speed over its value, square everything that has to do with speed, including its power, and then do the same thing for the radius. The power of the radius, that's taking the spot of b, times the fraction of the uncertainty of the radius over the value of the radius, and then square that whole term. So that's how you use these propagation formulas.